So yesterday we were seeing this result that tells you that if you have a ring R, and here I mean a ring with unity, and an element, just a second. Yes, oh, okay, for such a ring, yes. So recall that this ring R is a ring with unity and has characteristic 0, so that it contains the integers. So if you take an element alpha of such a ring R, the following are equivalent. The first is that alpha is a root of a monic polynomial with integer entries. The second is that the extension of z by alpha, that is the set of values of all integer polynomials of alpha, which is a subring of R, is finitely generated as an abelian group. There is as a Z module. There is a finite number of elements of R of Z alpha actually, such that every element of sorry. So I caught a mistake here. That's Z alpha. I should repeat this. No, this is okay. Sorry, I caught a. So yeah, that's a mistake. So this Z alpha is finitely generated as a Z module. There are a finite number of elements of Z alpha, such that every element of Z alpha is a Z linear combination of this gamma I. Okay, sorry. So I'll repeat this at the beginning of the next lecture of these boards, so that we note the correction. In the subring, and the third equivalent condition is that the subring Z alpha is actually contained in a finitely generated Z submodulo of R. Okay, so the fact that it's contained in such a submodule makes this also finitely generated by properties of Z. The fact that Z is a PID. Good. So we have these three equivalent conditions. Remember, for the ring R, this was written on the previous board for a ring with unity, commutative ring with unity in characteristic 0. And so the definition. Let's revert to black. Definition: an element alpha satisfying these equivalent conditions is said to be integral. Okay, so integral means say to be a root of a monic polynomial with integer coefficients, or satisfies the other equivalent condition. There is an important particular case. If the ring R is the ring of complex numbers, then an integral element alpha of C of the complex numbers is called traditionally an algebraic integer. And note the important difference because we studied in algebra algebraic elements. These are elements that are roots, elements of, say, the complex numbers that are roots of polynomials with coefficients in the rational numbers. And of course, you can multiply by the denominators and get that they are roots of polynomials over the integers. But here we are requiring these to be roots of monic polynomial with integer coefficients. And there is an important consequence, which you know already from the algebra courses, but it's since it will play an important role in the following, it's better to repeat it. So if alpha in Q, so of course Q is a subring of C, is an algebraic integer, then alpha is an integer. There is alpha is in Z, okay? So the only elements in Q that are algebraic integers are integers. Whereas, of course, first a comment, okay? If you have a rational numbers where, of course, A and B are in Z and B is different from 0, then this fraction is a root of the polynomial bx minus a, which is an integer polynomial, a polynomial with integer coefficients. But of course, if b is different from 1, this won't be a monic polynomial, okay? If b is 1, then this is an integer. And of course, this means that this is just a, and we are simply saying that a is a root of x minus a. But if b is different from 1 and minus 1, say, then we discover that this rational numbers is root of this polynomial, which is not monic. And what we are going to prove here, there is not only this is not a monic polynomial, but there is no monic polynomial of which alpha is a root. Okay, and let's see the proof. This is a well-known fact, but so first of all, we write alpha as, let me write it P over Q, where I don't mean P and Q to be prime, but of course, where I take the greatest common divisor of P and Q to be 1. So I take I take a reduced fraction, okay? In Italian, we say ridotta ai minimi termini. And then let alpha be a root. So P and Q are integers, of course. Be a root of the monic polynomial x to the n plus an minus 1 x to n minus 1 plus and so on plus a 1x plus a naught, a polynomial with integer coefficients, okay? So we substitute alpha and we get p to the n q to the n plus an minus 1 p n minus 1 q n minus 1 and so on plus a1 p over q plus a naught is 0, okay? So we multiply by q to the n. Okay, and find what? Well, all denominators vanish, and we have p to the n here, and then here, since you have q to the n minus 1 in the denominator, there will be a q coming out. Let's write the next term. So here we have pn minus 2. There's I haven't written it, but there's a qn minus 2 at the denominator here. So a q square is left when you multiply by q to the n. And so you get here, and okay, the sum of these two exponents has to be n, of course. And so we get p to the qn minus 1, and finally, okay? And now you note that q divides all the terms in red, okay? And so if you take, say, p to the n to the other side, and thus q divides p to the n, okay? But the fact that p and q are coprime implies, implies that q divides p, which is impossible because they are coprime, unless q is plus or minus 1. Okay, let's do it like this. I mean, we have a fraction, and we can always assume that q is greater than 0, okay? Because if there is a sign, you can discharge it on p, so q is 1. Okay, so this means that alpha is in the integers. And then there is another fact that I'm not writing down. If you now look at this, q has become 1, so q is not here anymore. You find that p divides all the terms in blue. Okay, so p divides a naught. So if you have an integer, which is a root of a polynomial with monic polynomial with integer coefficients, let's say if you have a polynomial with integer coefficients, a monic one, then any integer root will be a divisor of a naught. So for instance, if a naught is 1, you can be sure that the only integer solution could be 1 or -1, okay? Not that they have to, but there is no other choice. I mean, if a naught is 2, then the only possibility is 1 -1, 2 -2, okay? So this restricts the possibilities. Good, so we have seen that there aren't, the only algebraic integers which are in Q are the integers. So remember, all elements of Q are algebraic over Q, trivially. They are roots of integer polynomials, but only the integers are roots of integer polynomials with monic integer polynomials, okay? So we might think, well, okay, A over B is this is a root of the, if B is not 1, then this is not monic, but perhaps there is a monic polynomial somewhere else. No, this is not possible, okay? The only possibility is when B equals 1. Good, and there is an important property that of algebraic of integral elements. Let me think. Okay, I'll prove this later. Just a second. Just a second. No, this part can wait. This part can wait. So the important property I want to prove is the following proposition. So let's recall all the assumptions you have on R, okay? Let R be a unital commutative ring, so a ring with unity, of characteristic 0. So remember, the latter hypothesis of characteristic 0 means that R contains Z, and so we can talk of integral elements. And then the set of integral elements in R is a subring of R. So essentially, we are saying that the sum and the product of two algebraic integers is an algebraic integer. Whereas, for instance, the fact that one is an algebraic, is an integral, sorry. And if an element is integral, then clearly the opposite is integral. It's just a matter of polynomials. Okay, how do you prove this? Well, let alpha and beta be integral elements. Okay? And then consider the subring Z alpha beta of R. What's this? This is the smallest subring. You will surely encounter this in other courses in commutative algebra. This is the smallest subring of R. We contain Z and alpha and beta. And as in the case of simple extensions, Z alpha, this is the image of the polynomial ring Zxy under the map which is completely defined by, so the zxy to r, which sends x to alpha, y to beta, and an integer, say a, to itself, okay? So it's just the image of its evaluation in alpha beta, okay? I mean, in the case of univariate polynomials, polynomial is in one variable, we had a similar result, that there is a unique morphism of rings. Okay, so you have alpha and beta integral. What I want to prove, I want to prove that Z alpha beta is finitely generated as a Z module. Because then I will apply the result that I recalled at the beginning of the lecture, and to the effect that all elements of this, I'll repeat this at the end of the proof, all the elements of this subring will be integral, and this means in particular alpha plus beta and alpha times beta will be integral because this is a subring, so it's closed under sum product. So I want to prove that this is finitely generated. And this is actually quite straightforward because you see, first note that let's do it first at the level of polynomials. A polynomial in Zxy, this is actually one of the possible ways of constructing polynomials in two variables, starting with polynomials in two variables, can be written as a sum I from 0, say, to k. So you can write it as a polynomial in y, which coefficients that are polynomials in x. Okay, so essentially you isolate the powers of y, and then what's left will be the polynomials in x. And this means in particular that every element applying the morphism that I was discussing of a minute ago, every element of Z alpha beta is of the form, because since it's the Z alpha beta is the image of that morphism or something like that. Okay. Now the point is, yes, these are in Z, and K is a natural number. You see, apparently K is unlimited, but this is not really the case when you look here, because as beta is integral, okay, beta is a root of a certain polynomial, I would write as xn plus bm minus 1 xn minus 1 plus b1x plus b naught, which lies in the integer, with these integer coefficients. And look, it's monic, okay? The coefficient, sorry. Okay, let's fix this. It has become an m, okay? I'm circling it because well, let me circle this in red, because I made a change, so you notice the change, because I changed my mind from here to here. I wrote n here and m here, so let it be m. Okay, but so what does it mean? It means that let's call this polynomial. Let's call this polynomial b, okay. And then you note that since this is a monic polynomial, you can divide this polynomial here with a called, well, whatever, g, capital G. So dividing G by B in ZXY, okay, you can divide it because this is monic. So in general, you cannot do division of polynomials in Z, even in ZX, and in particular, you cannot do it. Yes, okay. So you do it here because this is, you consider this as the ring of polynomials in Y with coefficients in ZX. Okay, so this is a ring of polynomials in Y with coefficients in a domain. Okay, usually you cannot do divisions, but since it is monic, you can. So this means that let's write it the next page. That you can write G as Q times B plus a certain R, where what's important that either R is 0 or R has degree. In Y, because we are seeing this as a polynomial in Y, which is less than M, which is the degree of the polynomial B. This is a polynomial in Y, okay? Let's look back just for a second. So this B, these polynomials of which beta is a root, G is this biggish polynomial, okay? So what we found, this G was a polynomial running from I equals 0 to K, but when you evaluate, you don't need to go up to an arbitrary K, where K could be any natural numbers, because now evaluate in alpha and beta, okay? And you find that this vanishes, okay? And then B of beta is 0 by definition. So what we have found, we found that the elements of Z alpha beta can be written as in the form sum A from 0 to n minus 1 Fi alpha, say, and beta to the I, where m is fixed this time. M is the degree of B, okay? And now, if you do exactly the same thing with alpha, okay, similarly, alpha will be a root of a certain polynomial we call A, and this time we use n, okay? With integer coefficients, and dividing each Fi, I mean this thing here, which used to be polynomials in X, by A, and evaluating for X equal alpha, we find that that all, say, Fi can be taken either 0 to B, either 0 or of degree less than n. It's a similar, very similar to what we did with beta and the polynomial B, and here we do it with alpha and the polynomial A. So this means that every element of Z alpha beta can be written in the form Okay, let's use first the form. So we know already that we can take this sum up to m minus 1, where m is the degree of beta, of the degree of b. And then now we know that these polynomials can be taken of degree less than n, okay? And so this means that this will be a sum from I to 0 and to m, and j from 0 to n to minus 1, okay, of what? A certain coefficient, Cij, and then alpha j, beta e, okay, because I have expanded this polynomial fi, okay? This polynomial fi a degree at most less than n, okay? So this means that the j here, let me rewrite it because it was particularly unclear, the j here can be at most n minus 1. With Cij integers. Okay, so I've simply expanded this polynomial fi, and you see what's written here. Here it's written that all elements of z alpha beta are linear combination of integer coefficients of these elements, of which there are at most, because some of them may be the same, n times n. Okay, because the j goes from 0 to n minus 1, and I goes from 0 to n minus 1. So, in other words, so z alpha beta is generated as a z module by the, at most, n elements, alpha j, beta I, where j goes from 0 to n, and I goes from 0 to n, okay, where the top value is not taken. And remember, this is the degree of A, the polynomial, the monic polynomial, a monic polynomial of which alpha is the root, and this is the degree of beta, of B, okay? So this is a finitely generated module. This means if gamma is in Z alpha beta, and remember this is a subring of R, subring of R, okay? Then, of course, since this is a subring contained in Z, then zeta gamma is contained in Z alpha beta, okay? And by the proposition that I recalled at the beginning of the lecture, this means that gamma is integral, okay? Because Z gamma is contained in a finitely generated Z module, okay? So gamma is integral. Okay, in particular, alpha plus beta and alpha times beta, which are in Z alpha beta, because this object is a subring of R, okay, are integral. Okay. And so this means that the sum and the product of any two integral elements are integral, and then this proves the fact that I claim here that the integral elements form a subring of R. Okay. Allow me a little diversion. There is a proof that you might have seen, but it's very nice, and I'd like to give it. It's something about algebraic integers. So we are moving to C, okay? And this is a theorem, a proposition, which tells you let S containing Z be a subring of the complex numbers, okay? And suppose S is a finitely generated Z module. Okay? Then all elements of S are algebraic integers. So this proof requires to be in C. You'll see in a second why. But it's a nice proof. I mean, as you see, there's always this fact that there is a finitely generated Z module, which played a role in the proof we just saw. So the proof is very nice. That's why I want to give it, although it's a slight diversion. So suppose S is generated as a Z module by elements, let's call them gamma 1, gamma t, okay? So this means that every element of S can be written not uniquely, not necessarily uniquely, well. So it's not like in a vector space, as a linear combination as any element S of S, okay? S, linear combination, so some coefficients, let's call C1 gamma 1 plus CT gamma t for some Ci in the integers, okay? So we are not saying that this is a basis, so the expression may not be unique, but definitely you can do that. I want to prove that all elements of S are algebraic integers, and this means that they will be the root of a monic polynomial. So how does this monic polynomial, where does this monic polynomial come from? So let alpha be an element of S, okay? And then for each I, alpha gamma I will be in S, because S is a ring, the gamma I are in S, okay? And so the product is in S. And we know that every element of S can be written a linear combination of the gamma I. So this means that if you take alpha gamma 1, this will be a linear combination of the form, let's say, A11 gamma 1 plus A12 gamma 2 plus A1t gamma t, okay? And the same goes if you multiply by gamma 2, you'll have A21 gamma 1 plus A22 gamma 2 plus and so on, plus A2t gamma t, until you get to alpha gamma t, which will be A31 gamma 1 plus A T2, this is 2, gamma 2 plus ATT gamma t. But then look, let's write this in vector form, okay? So this here is alpha, which multiplies this vector. This we can do because we are in the complex numbers, so these are vectors in C to the t, okay? Column vectors. And what do you have here? Well, look, this is, you recognize matrix multiplication here. So this is the matrix, matrix multiplication. Times gamma 1, gamma t, okay? The row times column. But what do we have here? What you have written here is that alpha is an eigenvalue of this matrix. Let's continue here. Of the integer matrix A given, well, this matrix there, okay? It's a matrix with integer coefficients because our claim is that S is generated as a Z module by gamma 1, gamma t. There is every element can be written as linear combination with integer coefficients of the gamma I, okay? But then if alpha is an eigenvalue of this integral matrix, then alpha is a root of the characteristic polynomial of A. And to have it appear in the right form, I will write the characteristic polynomial x times the identity minus A. Sometimes it's written the other way around, but then it's not monic. And this is, of course, a monic polynomial because this is a polynomial we start with x to the t, okay, plus something, which is a monic polynomial with integer coefficient. Okay, that's clear. I mean, if you look at how you develop this determinant, you see that there is an x to the t. Okay, so this means that alpha is an algebraic integer. Okay. Okay, now that we have proved these facts, we can have a first application of our theory to prove this important fact that I had announced already yesterday. Theorem: if chi is an irreducible character of the group G, of course our groups are finite, then the degree of the character, the dimension of the underlying vector space, divides the order of G. Okay, and this is important because we have not used it when constructing our character tables, but of course restricts severely the kind of irreducible representation you might be looking at. So how do you prove this? Well, we'll take take the long way. No, not quite. So we know that the center of the group algebra, of the complex group algebra, okay, is say the vector space. This is a ring in algebra. Is the vector space which has as a basis the sums of the conjugacy classes. Okay, so a base of this vector space of the center, okay, the center of the complex algebra as these sums as a basis. So recall that if C is a conjugacy class, if C is the conjugacy class of G, of the element G, little g, and this is x1, xn, we say distinct elements. So this is exactly a class with n elements, because I mean I cannot simply write these elements here, because you know that in a set, if all elements are equal, you just have one element. Then one of the basis elements would be what I'll call sum over C, and this is simply this sum. Okay. Okay. So since this is a subalgebra of the complex algebra, if we take the product of this of two of these, so CD two conjugacy classes, okay, this will be a linear combination with complex coefficients of the conjugacy classes, of the conjugacy classes, because this is a subalgebra as a vector space as a basis, which is given by the sum. So this will be a sum over E, the conjugacy classes, of of this conjugacy class with certain coefficients, which are called CDE. Later, we will see that we can even compute these coefficients using characters. There is a somewhat involved formula due to Burnside, which proves what these coefficients are. In principle, these coefficients are in C, because all we know is that this vector space, this is an algebra is a vector space with basis the sum of conjugacy classes. But if you look at what's happening here, okay, let's copy this and then we'll continue on the next page. If you take this formula here, okay, I'll rewrite the E on the other side, add to new page, okay? So this is the sum over E, and let's see whether I can, no, I cannot erase this, but I can say that this is not important. So, I mean, if a C is gx1, gxn, and D is equal to hyy, hym, say, distinct elements. Okay, so what we are doing here, we are multiplying these elements, this element, times this element. Okay, so, and of course, this will be, I'm not writing the details, but that will be the sum of all the products. Okay, so if say K is an element of A certain conjugacy class, lambda CDE counts how many of the products? GXI times HYJ equals K, okay? Because I mean, yes, I mean, if you have a K here, this K here can only come from a product of a GXI with a Y with a HYJ. And so this means that this has to be a non-negative integer. Is a non-negative integer. Okay, because so let's check what we are doing. In principle, I know that the product of this is again in this subalgebra, in this subring of the complex algebra. So it's a linear combination of the conjugacy classes. Sorry, there's a misprint here, which I have to correct also. Sum over E. Okay, it's the sums that are the basis. Okay, and so here too I have to replace this by sigma of E. So if a certain conjugacy class appears here, and then K is an element that appears here, it means that it has appeared as a product of an element here and an element here. And so this thing here is counting the ways, how many of this product equals K. And then it has to be any non-negative integers, because either you don't get K, and so the class E does not appear, or it occurs in a natural number of ways, I mean, in certain products. Why is this important? Because you have that the product of two conjugacy classes is a linear combination with integer coefficients, actually non-negative integers, of the conjugacy classes, which means that, so let's say, let me think. So this means, thus, the set of, okay, say, the linear combination of the conjugacy classes with integer coefficients. Okay, so C ranges in the conjugacy classes. Where AC is an integer, is a subring of say of the center of this. But then also, okay, why the center? Because this is a commutative ring, is the center, a commutative ring with unity or characteristic 0. Okay, and what's important, you see, this is, and the set which we call possibly S, and S is finitely generated. I mean, it's written here. S is the set of linear combination of the sums of the conjugacy classes with integer coefficient. It's finitely generated as a Z module by the elements sum over C, okay? Where, because the conjugacy classes of a finite group are of course finite. So what does it mean? Thus, this is a finite generated Z module. All of its elements are integral. Okay, in particular, all sigma C are integral. Note that this is a quite indirect proof. So we have proved that the sums, if you take a conjugacy class and you take the sum of its elements, then this is an integral element. So it will be a root of a monic polynomial with integer coefficients. We have not, however, named this polynomial explicitly, okay? We just know that there is such a polynomial, but we haven't named it explicitly because we are going indirectly through this important thing that finitely generated as a Z module is enough to prove integrality, okay? Good. And why is this important? Well, because now consider the following. Okay, let f from G to C be a class function whose values are algebraic integers. Okay, so a class function whose values are algebraic integers. Then, of course, each fg is an algebraic integer. Of course, this fg is in C, but you can say see this is an algebraic integer as an element of C. But such an fg, fg times 1 is an element of the center of or actually, yes, of the center of the group algebra, because it's a multiple of 1, which is of course a scalar multiple of 1, and so this is an integral. Okay, in this ring. No, not Z. Sorry, this is center. Okay, sorry, not Z. I hope I haven't made this misprint, the mistake before. Okay, so this is integral. But remember, so what we have found, I mean, it's an algebraic integer, so it's a root of a monic polynomial, and of course you multiply by 1, which is the 1 of G. Of course, it's still a root of exactly the same polynomial. Okay, so we have that this. No, what's up? Okay, there must be. Oh, there's an empty. Okay, let me delete this page and. No, let me not delete this page, otherwise I make a mess. I'll delete it later. So we have proved that all of these sums of the conjugacy classes are integral, and we have proved that, well, which is rather trivial, that if you have a function with classes values are algebraic integer, all the values are integral. But then, mixing the two together, we know that integral elements form a subrings of the center, okay, written correctly, of CG. We have proved before form a subring of it. And so this means that you can take sums or products. So the sum of Fg, say G in G is integral. If f is a class function, okay? Because if f is a class function, recall, this means this is constant over classes. So this is a linear combination with coefficients, with certain coefficients of the sums of the conjugacy classes, okay? Because you can rewrite this as the sum, okay, in red, of the conjugacy classes Fg sum over C, where G is in C, okay? Because this is a constant over the conjugacy class. So it's the same for all elements of the conjugacy class. So, okay, so you see, this is a sum of products of elements that you know are integral. This sum is integral and this is integral. Okay? But then we can apply our familiar isomorphism from C of G to recall the sum of what we have recently called and Vk, or where chi ranges over the reducible character. So the Vk are the distinctly reducible modules. And this applies to, in particular, to the center, because we are talking elements in the center. And recall, this goes into the sum over chi of the reducible characters of the centers of this. We remember this is a matrix ring. And so this is made of scalar matrices, okay? And so if you take such an element, and actually what you do, you consider something we have already seen earlier. You can project on one component, okay, for a given chi. So you can project in particular here on a single center. And so if you do this, you'll end up with a scalar matrix. So this means applying rho for a given chi afforded by rho. Okay, so this will go to this element, which is a scalar matrix. And here I'd better check. Yes, it's something we saw the other day, which is scalar matrix lambda, 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 okay, where lambda is nothing else but the sum over G, for G in G, of fg chi g over chi 1. Okay, this we calculated yesterday. Okay, so this is what we found. And recall, this can be written compactly in this form: order of g divided by chi of 1 times the inner product f and chi conjugate. More about this chi conjugate in a second. Okay. Okay, so the image of this is this element, which is in the center, because this element is in the center. And so this is a scalar matrix, because we ended up in a matrix algebra, and the center of it is made by the scalar matrix. And this scalar lambda we computed, and it equals this thing here. Okay. Just a second. Yes, okay, fine. So this holds, okay, for every class function. Oh yeah, no, this is, sorry, I'll rewrite this in a second, but first another important thing. So recall that we had made this integral, okay? But when you apply essentially rho to this, you go here, this remains integral, okay? Because this element here, call it alpha, okay? This alpha is a root. Next page. Alpha is a root of a polynomial, of a monic polynomial. Say x to the n plus n minus 1, xn minus 1, plus and so on, plus a naught with integer coefficients. So, okay, this is a bit cumbersome, but so this means that that when you compute this polynomial in alpha, evaluate in alpha, you get 0. Then you apply rho, which is a morphism. And so if since it's a morphism, you'll get the following, and this you get an minus 1. Why do you do that? Because rho is linear. Okay, remember that rho is a linear map. Wait just a second. Well, yes. Yes. Okay. So we had rho. No. Okay. So rho was going from G to GLV, and then we extended it there to a map CG from to NV, where you send a linear combinations of elements like this in the same linear combination applying rho to G. Okay, that's the way that's the universal property of the group algebra. You have a morphism of groups from G to GLV, which is contained in NV, so a morphism of monoids, and you extend this to a morphism of algebras by defining the map of a linear combination, leaving the coefficients untouched and applying rho to the element of G. So this is, apply rho means this, going from this morphism, which is in GLV and then in particular in NV, to this morphism of algebras, okay? And so you see what we have here. This means rho of alpha is integral in the center of the endomorphism algebra of the chi, okay? So you started with alpha here, you apply this, you get in the center here, but rho alpha is nothing else but this lambda, 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 okay? So to say that rho alpha is the root of these polynomial means simply that lambda is a root of this polynomial. let's call A this polynomial, or the polynomial A. Obviously, I mean, because what it means to apply to evaluate this polynomial in this matrix is simply, so say A evaluated in, this is 0. Okay, if you evaluate this polynomial A in row alpha, we saw that this is 0, but this is nothing else but A lambda and so on, A lambda. Okay, of course, because that's the way you compute with scalar matrices. So to say that row alpha is the root of the polynomial A means that each lambda is the root of the polynomial A. That is, lambda is an algebraic integer. Because an algebraic integer is nothing else that a complex number which is integral. There is a root of a monic polynomial with integer coefficients. Okay, so what we have found that if you start with a class function whose values are algebraic integers, you take this element here and you obtain, you apply this, and you end up with a scalar matrix where lambda is an algebraic integer. So this thing, which I'm going to copy presently, so this thing, which is lambda, add to library, and then I'll go to a new page, and I'll copy, just a second. Okay. And how do you let this disappear? Just a second. There's too much. There's too much. Okay, yes, here. This was covered by. So this is lambda. Okay. And we know that this is so this is an algebraic integer. If f from G to C is a class function, so a function that is constant on conjugacy classes with values whose values are algebraic integers. So we have to take, we are now going to take a special function of this kind. Let f be chi conjugate. A word about that in a second. I claim that this is an irreducible character. And then what we found, okay, first of all, is this a class function? Yes, this is a class function, like all characters. Are the values algebraic integer? Yes, because remember that if you take the image of any element under a representation, this can be put in diagonal form. Okay, this is something we saw at the beginning of our lectures, where omega I are roots of unity. And of course, these are algebraic integers because they are a root of something like xn minus 1, okay? So monic polynomials with integer coefficients. And of course, the character of chi of G will just be the sum of this. And the sum of algebraic integer, so an algebraic integer. Okay, so you plug this here and you find that thus lambda equals of order of G over chi1, chi bar, more about this. This is an irreducible character, so what the inner product with itself is 1. So this is an algebraic integer. Okay, but of course, this is the quotient of the order of the group, which is an integer over the dimension of the underlying vector space, the t in this case particular. So it's also an integer, and the rational number. But we proved, we recall this fact that you no doubt knew very well, that this implies that this is an integer, okay? And this means exactly, this is the very first lecture of algebra, that is, chi1 divides the order of G, okay? Because the quotient is an integer, so you take it to the other side, and it means that chi1 divides the order of G. So this might have looked a bit involved, but if you look at it, the ingredients were all in place. In particular, the very important isomorphism, these isomorphisms here, which you've seen has been extremely important, because you have a sort of unknown object with this group algebra, and here, whereas here you have matrix rings. I mean, if you project on one component, you have matrix rings, and here scalar matrix is something very elementary. Okay, and the fact and using algebraic integers, again, if you speak of a group by itself, I mean, if you study the group by itself, there's no number, no complex numbers anyway. But if you start looking at the representations, then you find yourself in the realm of algebraic numbers. I mean, because of this very reason that we studied, that we discovered at the beginning of the course, that the image of if an element has order n, say, then it can be put in diagonal form with the omega I on the diagonal, which are nth root of unity. And so in particular, the character is an algebraic integer, because these are algebraic integers. So representations allow us to discover that there are complex number, algebraic integer, associated to a group and its element, and allow us to study, to use these integrality properties to prove facts like this, that, well, of course, this is a fact about the character itself, but still, I mean, okay, just a comment about this conjugate, which I haven't discussed very much in detail. So if I must have mentioned this, but let's take an irreducible character. Well, in part, I could do it with any character. Okay, then I claim that two things, that if you take the conjugate of this, I've already used this, but let's do it again. The conjugate of the character is the value of the character on the inverse, and moreover, chi bar defined by chi bar of G equals chi of G bar is again is also an irreducible character. Okay, so this 1 and 2, I probably mentioned this already, but let me do it anyway. So the first thing is simply due to the fact that if rho is the representation affording chi, so this means chi is the character, is a trace of rho, okay? And G is in G, okay? Then as we saw, rho of G can be written as, and G is, say, of order n, or n could be the order of the group, I mean, it's not important. Then we saw that you can put rho of G in this diagonal form, okay? Not a scalar form in general, of course, just a diagonal form, because of the reasons that we had discussed a couple of times, several times during the course. And so of course, the character of G will be the trace of rho of G will be omega 1 plus omega t. Okay? Now, what's rho of G inverse? Well, this is, since rho is a morphism, is rho of G inverse, which, of course, this being a scalar matrix. Yeah, I'm sure, I'm sure I've discussed this. These are the inverses. But the omega I are roots of unity. And as we discussed several times, if you have a root of unity here, its inverse will be its conjugate, okay? The omega I are roots of unity. So omega 1 conjugate, omega t conjugate. And so the trace of rho of G minus 1 will be just this, okay? And of course, this is just the character evaluated in G inverse. Okay, because the trace will be the conjugate of the value of the character. So that's the one. And as to 2, why is this an irreducible character? There is a, well, the funny way is this. So chi bar of G, so chi bar on G is defined like this, is a class function from G to C, okay? And as such, you know that a basis, we saw that using the orthogonality relation, that the basis of the space of class functions from G to C, whose basis is provided, of which a basis is provided by the irreducible characters. So this is a class, if chi is a class function, because chi is irreducible, then its conjugate is still a class function, it's constant of the class. So this means that chi bar of G is a linear combination with certain coefficients, okay, coefficients a psi, say, psi of G, where psi ranges over the irreducible characters, okay? Now we started with chi, which is irreducible, okay? This is sort of an exercise on things we have already seen. And this being irreducible means that chi, the inner product is 1. And this inner product is nothing else but, well, of course, 1 over G, this average, which we have seen we need. And then the sum over G and G of chi, the conjugate of G, and then chi of G, okay? But you can rewrite somewhat perversely this in this form. Chi G will, of course, be the conjugate of the conjugate, okay? Why is this important? Because if you look at this expression, okay, this is nothing else but chi bar. So chi bar, the inner product is still 1. And this means that chi bar is an irreducible character. I must have mentioned this already, but because if you do chi bar, okay, which is this product, you'll find that this equals a psi square, okay? And so this means that, yes, I think we have already seen this thing. And this is 1, and these are integers. Actually, let me see, just a second. Well, okay, let me do it. So we found that a psi has to be 1 for exactly one psi, and then since you find easily that this has to be greater than 1, greater than 0, because when you evaluate in 1, you find that this is positive. Okay. So you found that chi bar of G is A psi for some psi, and psi of G, if you evaluate in 1, which is a positive number, and you find, and this is also positive, so this has to be positive, and so it has to be 1, okay? I hope this is clear, but I think it's not the first time I discuss this. So the conjugate of a reducible character is still an irreducible character. Of course, I wanted to do this somewhat perverse proof going through the inner product, but you can also simply consider that if rho is a representation, possibly reducible, then the conjugate, rho bar is also a representation. Say irreducible if this rho is reducible. I leave this as an exercise where what's rho bar? Well, if rho of G is, I'll write just some numbers. Okay, then rho bar of G is simply what you get if you apply the bar, the conjugate, the complex conjugate to all elements. And of course, chi bar of G will be the trace of rho bar of G. And this will provide another proof of this fact that the conjugate character is still the conjugate of an irreducible character is still an irreducible character. But this proof here is somewhat more conceptual. I mean, if chi is 1, then chi bar is also 1, and this means by this argument that I've been a bit sloppy here, but I don't think it was the first part. I mean, this property characterizes irreducible characters in the space of all class functions, okay? I think this is not the first time I mentioned this, so. Good. Let me see whether there is something fruitful I can do in the, sorry, next. In the 10 minutes or so that we are left with. Okay, yes. So the next thing I want to do, but I won't be able to prove this today, but I want to exploit this the integrality to prove the following. Let chi be an irreducible character, chi1 different from 1, okay? So this means, in words, chi is not a linear character. And recall that a linear character is nothing else but a morphism from G to C star. Let's recall it here. So if chi is linear, there is chi1 equals 1. Then chi, I recall this means that the representation has dimension 1. So you are attaching to G a matrix of dimension 1, which means a number, a complex number, between a non-zero complex number between brackets, between square parentheses. And so then chi from, which is just the number inside, is a morphism from G to C star. To C star because we are taking invertible matrices. So what's a 1 times 1 invertible matrix is just a non-zero number, complex number surrounded by brackets. And in particular, so chi G different from 0 for all G. So if chi is linear, then all of its values are different from 0. But if chi is not linear, then there is G in G, such that chi of G is equal to 0. We saw this happening for instance, in S3, okay? And now we can see that, no, just a second. We can see that, we will see that this is a general fact. What I'm able to do today with the time left is just to give an introductory result, which is, let me see, just a second, which is the following. Yes. So it's not surprisingly, it's a fact about algebraic integers or the like. And so the lemma says the following. Let E be a subfield of C. Okay? Actually, okay, sorry. Let's be more quick. Let E of Q over Q be a Galois extension. Okay, with E containing C. Okay, so E is a field containing Q and a subfield of C, and this is the Galois extension with Galois group abelian. Okay, then for alpha in E and G in the Galois group, we have that if you the absolute value, the norm in the complex numbers of alpha to the G, so G is the Galois group, so it permutes the element of E, equals to this, to you can take it the G out of the absolute value of the norm of a complex number. I mean, if the complex number is x plus I y, this will be the square root of x squared plus y squared. Good, so let's see why this holds. And then I don't have time today, but I will show that if the Galois group is not abelian, this does not hold anymore. Proof. So E over Q is Galois, okay, which means it's invariant under all automorphisms of C. Well, yes. In particular, we will have no, sorry, what am I saying? In particular, E, yes, E equals E conjugate. E is invariant under conjugation. Complex conjugation. The reason, for instance, is that such an extension is a splitting field of a polynomial or a rational polynomial. And of course, if you have a rational polynomial, if an element is a root of the polynomial, then its conjugate is also a root because the rational numbers are of course self-conjugate, okay? So let C, which is an element then of this Galois group, be the restriction to E of complex conjugation. So this means that if alpha is in E, alpha to the C is simply the conjugate of alpha, okay? So again, since this is Galois, then it's invariant under conjugation because it's a splitting field, for instance. There will be probably simpler ways. So, okay, so what we want to prove that this absolute value, this norm, equals this. Of course, this is a positive number, so I can square it, and if I prove that the squares are equal, then the numbers will be equal because these are positive numbers. Okay, so we start with this. Okay, and what's this? Well, the square is simply the product of a alpha g, sorry, times the conjugate. Okay, so remember that the norm of x plus iy is the square root of x squared plus y squared, which is the square root of x plus iy times its conjugate x minus iy, which is the conjugate. Okay, so if you take the square, it's a product of an element and its conjugate. Okay, but recall that the conjugate, we call C this element of the Galois group, the restriction to E of complex conjugation. So you first apply G and then you apply complex conjugation. And the important assumption is that this Galois group is abelian. Okay, so this means that you can, well, you can first switch to black, and then you can exchange these two, okay? Because the group is abelian. This is a product, a composition in the Galois group, product in the Galois group. So since it's abelian, you can exchange this. And now what you have here, G is an element of a Galois group, so it's a morphism, which means you can take it out. Well, come on, black. Okay, you can take it out because G applied to a product is the product of the G's. But what's this? This is alpha times alpha conjugate, because C is just the restriction of that, and this is exactly alpha alpha square, say, to which you apply G. And yes, and if you wish, since G is a morphism again, this will be alpha to the G square. And as I said, this stuff here, these are positive numbers. So if the squares are equal, then the numbers themselves are equal. Okay. But I'll start next lecture on Monday with proving that the assumption that you have used here, that the Galois group is abelian, is essential. Okay, there will be a simple example of a Galois extension containing C, where the group is non-abelian, and then this equality does not hold. But this equality will be important in proving this result about vanishing of value of characters. Good, that's all for today. There's nothing particularly useful I can do in the couple of minutes remaining. So thank you, and see you next Monday.